In this video, I'm going to work through the worksheet in our packet from 1.1, and we're going to compare two cars given their distance. So the graph in the figure 1 represents the distance from a given location of two cars A and B traveling in the same direction on the same road. And before I even read the questions, I'm going to look at my axes. So I notice that my vertical axis is the distance from the starting point. That's important. And that's in miles. And I notice that my horizontal axis is the time, and that's in hours. And there's a nice key where car A is going to be green and car B is going to be that black line. So this figure is the distance traveled by two cars. Pretty straightforward. So it looks to me like car A starts 0 miles from the starting point, whereas car B starts 20 miles from the starting point. So here I'm looking at their y-intercepts. These are their y-intercepts here. And then I notice that, at 2 hours after we start, car A is now 20 miles from the starting point, whereas car B is now, let's say 30 miles from the starting point, because it looks like it's halfway between 20 and 40. And 4 hours after we start, looks like both the cars are at the exact same distance from the starting point, 40 miles from the starting point. All right, so before we continue and answer any questions, I want to go over a couple of concepts with you. And the first one being velocity. So velocity is what I like to call the rate of change of displacement. Displacement is the moving of an object. So for example, these cars, they started at a certain point and then they displaced themselves a certain amount of miles every hour. Okay, so that's displacement. So velocity is the rate of change of that displacement. And both of these cars, their distance from the starting point is represented with a line. And how do we find the rate of change of a line? Hopefully this is coming to you. It's a very key word that we use in algebra, and it is the slope. So the rate of change is really the slope of the displacement. As long as we have lines, we can find slopes. This will get a little bit more tricky as we get into other functions, and that's where we'll use calculus. But if I was looking at the slope of any of these lines, let's talk about the units then. So we know that slope is change in y over change in x, or rise over run. So for this, it's going to be the change in the miles. So the numerator will be the miles over the change in the time, or the hours. So it's miles per hour. That'll be our units. Or miles per hours, and then you would just divide by whatever you needed to divide by to get it to miles per hour. All right, so now let's talk about instantaneous rate of change. Notice the root word in instantaneous is instant. So this is the rate of change, or the velocity, in an instant. And it's actually quite easy to find when you're dealing with linear functions. Instantaneous rate of change is going to be the same as the rate of change. So it's happening in an instant. How much time passes in an instant? Well, in an instant, no time passes, right? An instant is an instant, by definition. So if we're thinking about velocity here, and we want to know the instantaneous rate of change of displacement, if we think of this as the change in miles per the change in hours, well, the instantaneous rate of change is going to be as the change in hours goes to 0. right? Because no time is changing. It's happening in an instant. Well, that's weird. So then I would have the change in miles over 0. Isn't that undefined? So this is where calculus is going to help us in the future. I'm just kind of introducing this to you guys as a concept now because we are dealing with a beautiful graph here that will tell us velocity. And instantaneous rate of change of displacement gives us velocity. And again, in a linear graph, your instantaneous rate of change is basically just your rate of change. But when we get working with other functions, it'll be a little bit more tricky. Okay, so now I've introduced us to a couple of concepts, and really the only concept that we really need to understand here is velocity. Now let's answer the questions. Describe what is happening at t equals 2. So at 2 hours, we're going to describe what is happening. Well, I see that car A has traveled, it's now basically 20 miles from the starting point, and it started at 0 miles from the starting point, so it's traveled 20 miles. And I also see that car B, well, it's at 30 miles from the starting point, and it's traveled then 10 miles because it started at 20 miles from the starting point. So we'll say car A has traveled 20 miles. Car B has traveled 10 miles. All right, so which car is going faster? Let's talk about the miles per hour. So again, car A has gone 20 miles in 2 hours. So it's going 10 miles per hour. Car B has traveled 10 miles. So we've done 10 miles in 2 hours. Or it's going 5 miles per hour. So which car has gone farther? Car A has traveled farther, right? Car A has traveled farther. How about we do that? And how far apart are the two cars? Okay, so now we're talking about distance, and not distance traveled, just distance from the starting point. So why don't I start a table of values so that I can figure out the distances apart of the two cars. And then I think I'll do car A and car B. So at 0, let's see, car A was 0 miles from the starting point, and car B was 20 miles from the starting point. At 2 hours, car A is now 20 miles from the starting point, and car B is now 30 miles from the starting point. So it looks like they are, at 2 hours, they must be 10 miles apart. Let's just do a little line here. 10 miles apart. Moving on to number 2. Are the cars ever moving at the same speed? So speed is really another word for velocity, right? Velocity is in the units miles per hour here, and so is speed, right? So velocity, we could also say, hey, well, velocity is speed. Velocity is just speed with direction involved, and we'll talk about that. I think when we get to calculus, we talk about that. So are the cars ever moving at the same speed? Well, in order for them to move at the same speed, they would have to have the same slopes. They would have to have the same velocity. Do these two lines that represent the displacement or the distance that these cars have traveled, do they have the same slope, which again, the same slope would mean that they were traveling at the same velocity or the same speed. So are the cars ever moving at the same speed? Do they have the same slope? I guess that's the question we need to answer. And we're going to say no. Never have same slope or rate of change. Explain how the graph represents this event. It doesn't. They never are traveling the same speed because they never have the same rate of change or the same slope. Same speed, same slope, same rate of change. These are all the same in this model. So describe the location of the cars at time equals 0. Okay, well at t equals 0, let's see, we've already got this up here in my table of values. Car A is at the starting point. Car B is 20 miles from the starting point. How about I'll just put start. And what can be said about the speeds of the cars at this time? Well, that's a little bit tricky. I don't think that there's enough information for us to tell the actual speed of the cars at that time because we don't have any information before we started the timer. So what I mean by that is I would need these lines to continue. Then I could say, oh, look, it's constant the entire time. So that it still has the same slope. But what if these are piecewise functions? Or what if they were stopped at time 0? We don't know. Okay, so not enough information to assume the speeds of the cars. Does one car ever pass the other, and at what time? So car A is definitely going faster this entire time, right? Car A, let's go back to problem 1 or question 1. Car A is traveling at 10 miles per hour, and car B is traveling at 5 miles per hour. Why are they traveling so slow? I don't know. I did not make this model. I just think that this is a great model to kind of get you guys used to reading these graphs. So because car A is traveling twice as fast as car B, I would say more than likely it's going to end up passing car B. However, we can then look at the graph and we can say that at 4 hours time, both cars are at 40 miles from the starting point. And then at 6 hours time, car A now looks like it's at 60 miles from the starting point, whereas car B looks like it's at 50 miles from the starting point. So we can then say that car A definitely passes up car B. I'm going to fill out my table just to have some information. Sometimes looking at it numerically is helpful. I was just looking at it graphically. So we can see then, looking at our table of values as well, that car A is going to pass up car B. And have the two cars traveled the same distance at any point in time? And if so, when? Well, let's see here. Just because they're at the same distance from the starting point doesn't mean that they've actually traveled the same distance. So I would have to say no. And there's a good formula that relates distance, rate, and time. Distance equals rate times time. So the distance traveled will always be the rate, in this case the miles per hour or the velocity, times the time, times the number of hours, right? And this is just unit analysis, really. So the distance for car A is the rate. Well, car A is traveling 10 miles per hour. And what do we want to do? You want to do, how about 10 hours later? We could do this for any amount of hours. So the hours reduce and you're left with 100 miles in 10 hours. Car B is going 5 miles per hour. And if we do it after 10 hours, well, let's see, it's only going 50 miles. Right? Again, the hours reduce. Now, maybe you're asking yourself, but Frisk, or you're asking me, but at time equals 4 hours, they were at the same spot, so they had to have traveled the same distance. Well, that's not true, right? So car A started 0 miles from the starting point. So at time 4 hours, it's gone 40 miles. Okay, and at time for car B, right, it started at 20 miles. And then it ended up at time being 4 being 40 miles from the starting point. So it's only traveled 20 miles. Okay, so don't forget that. And if that's confusing for you, we can do these exact same equations, right? The distance of A, again, it was 10 miles per hour. And if we do that at 4 hours, all right, well, it's gone 40 miles. We knew that one. And then if I want to do the same thing with B, that's going to be 5 miles per hour times 4 hours. And again, that one's only gone 20 miles at that point. So using unit analysis to help us.